My name is Niels, and I'm from Aalborg University, Copenhagen, and I will briefly present our paper, Knock on Wood, combining redirected touching and physical props for tool-based interaction in virtual reality. But before I say anything else, I want to acknowledge the efforts of Patrick and Oana, two of our former master students who did all the hard work and turned the idea into a working prototype and ran the user study. So, while current virtual reality systems offer compelling audiovisual experiences, the sense of touch presents a significant barrier to complete immersion in virtual environments. Physical props, serving as proxies for virtual objects, offer a convenient and inexpensive approach to virtual touch. However, it's by no means trivial to rely on physical props as a source of haptic feedback in virtual reality, especially if users are offered a high degree of freedom to interact within complex virtual environments. In this paper, we argue that there exists at least 3 criteria for successfully deploying physical props in virtual reality. I'll briefly outline the 3 and provide a few examples of how these criteria have been addressed in the past. First, the criterion of sufficient similarity. Physical props should be sufficiently similar to the virtual objects they serve as proxies for, with respect to haptic properties such as weight, shape, size, and texture. This is impractical if a virtual reality application allows users to interact with different objects that vary with respect to their haptic properties. One approach to mitigating this problem is redirected touching. Redirected touching manipulates the mapping between the user's real and virtual hand movement during interactions, and thereby makes it possible for the same prop to serve as a proxy for different virtual objects. We refer to the second criterion as the criterion of complete collocation. The idea is that all virtual objects that the user may want to interact with should be represented by a physical prop. This necessarily means that the utility of physical props decreases in proportion to the number of virtual objects that the user can interact with. For that reason, it would be really useful to be able to repurpose the same physical prop so that it can serve as a proxy for multiple virtual objects. One way to accomplish this is through so-called haptic retargeting, which warps the virtual environment, the user's virtual body, or both. In this example, the user's virtual hand movement is warped, and because he compensates for this warping, he'll always encounter a physical cube when he reaches for a virtual cube. The third and final criterion is the criterion of compelling contact forces. So if the user touches an object that is influenced by contact forces originating within the virtual environment, then appropriate information about these forces should be transmitted to the user. So for example, if a grasped object collides with or scrapes against virtual objects. Here you see an example of so-called mutual human actuation, where 2 physical connected props are used to provide 2 users with haptic feedback in response to interaction in virtual environments. So here they are effectively addressing this third criterion. This brings me to the work described in our paper. We propose redirected tool-mediated manipulation, or RTMM for short, which uses visual dominance to address the criteria of compelling contact forces during tool-based manipulation in virtual reality. When users are grasping a physical prop that serves as a proxy for a virtual tool, then we introduce a second physical prop that serves as a proxy for the virtual object being manipulated using this tool. This second prop provides passive haptic feedback when the 2 props come into contact, and redirected touching is used to change users' perception of the interaction. So for example, we attempt to create the sensation of using tools to manipulate the shape and the position of virtual objects. We implemented 3 prototypes of redirected tool-mediated manipulation based on 3 different tools, namely a hammer, a screwdriver, and a saw. Here's a quick preview, but please refer to the paper for details. Redirected hammering manipulates the mapping between the physical and virtual hammer's vertical position to ensure that the user strikes the physical surface whenever the virtual hammer hits the virtual nail. Redirected screwing involves a similar type of manipulation and ensures that the physical screwdriver touches the physical surface whenever the virtual screwdriver is in contact with the screw. Finally, redirected sawing involves two forms of manipulation. That is, we offset the virtual saw in 2 dimensions to give the impression of one cutting through the plank, but also to ensure that the physical saw slips off the edge of the physical plank as the virtual saw cuts through the virtual plank. And to evaluate the developed prototypes, we performed a within-subject study with 20 participants, comparing 3 conditions for each tool in terms of realism, preference, and precision. So the 3 conditions we compared for each tool was interaction using a single HTC Vive controller, interaction using a single physical tool, so either a hammer, a screwdriver, or a saw, and interaction involving a physical tool and a physical surface based on where the interaction was made possible using redirected tool-mediated manipulation. So the participants experienced all 3 conditions for each tool, and they did so in blocks of trials, so 1 block for each tool, and this amounted to a total of 9 trials. And both the conditions and the blocks, the orders here were randomized. In the beginning of each block, before the participants put on the head-mounted display, they were asked to hammer a nail into a board, drive a screw into a plank, and cut through a board. This was meant to serve as a reference when evaluating the realism of the 3 conditions. So afterwards, they were exposed to the 3 conditions, which were presented in randomized order, as I just mentioned. So after exposure to each condition, we asked the participants to rate the perceived realism and perceptual similarity. So how close was the experience to the real thing they had just tried? And they did so using 4 7-point rating scales, where a high rating indicated high realism. So during each condition, we logged the participants' movement to determine how precisely they performed the task. For example, with respect to the hammer, we looked at how far from the nail the hammer was during each strike. This brings me to the findings, which I'll briefly summarize, but again, please refer to the paper for details. The 4 questionnaire items assessing perceptual similarity and perceived realism yielded similar indications. The participants generally found redirected tool-mediated manipulation to be the most realistic, and this condition was also the most preferred of the 3. Judging by the rating scales, the degree of perceived realism and the degree to which they resembled the act of performing or using the real tool differed between the 3 types of tools. So of the 3 tools, redirected hammering elicited the most realistic experience, but the redirected screwing was perceived as the least realistic. The measures of precision also yielded some interesting, albeit somewhat surprising results. That is, actually, we were a bit surprised to see that redirected tool-mediated manipulation did not appear to impair precision in any significant way. With that said, it is notable that the participants appeared to find it a bit harder to cut along a straight line when using the saw. So to conclude, in this paper, we introduced the concept redirected tool-mediated manipulation that combines 2 or more physical props and redirected touching. We presented 3 prototypes of this approach, and we presented a user study evaluating the perceived realism and precision of the 3 prototypes by comparing them to interaction using a single prop and a standard VR controller. Thanks for listening.